All right, so we are doing characteristics of functions. Yesterday we did this giant graphic organizer that kind of hammered out what these graphs look like, right? And the little details from each. So we're going to take what we learned yesterday, so keep this handy off to the side, and we're going to try and answer some questions about it. All right, so the first section is, these are called scatter plots, right? These are dots that are scattered along. This is really what real life data looks like. It doesn't necessarily follow a perfect line. It follows what's called a trend. So when we look at this first trend of dots, if you just kind of fit a line to it as best as possible, that, my dears, is a quadratic function, right? It's U-shaped. So U-shaped, so we'll circle quadratic. All right, this next one, if we follow the points, it's got this curve to it, kind of like a bow. So there we go. This is exponential. And again, this is a U-shape, so if it's U-shaped, it's quadratic. This one is linear form. And then this last one, not quite a U-shape, right? It's like half of a U-shape, so that would be exponential. All right, so now we're going to do some matching with some descriptions to pictures over here. Before we get into the descriptions, let's just kind of run through our multiple choice. Let's get our brains ready for this. This first one is a quadratic, right? Because it's U-shape. This one's linear because it's a line. This one is a J curve, exponential. It's like a bow to it, a bow. Exponential. This is linear. This one, don't get confused. It's not exponential. It is a U. It's not quite completed, but it is that U shape. So this is quadratic. And then here we have something increasing, so exponential. Kind of looks like a boomerang, right? So exponential, I don't know. All right, so let's see what we can do. Exponential function, all right, so we had two of them. And it has to always be increasing. Okay, so when we read these graphs, we read from left to right, just like we read sentences. All right, you want to read left to right. So when I look at this one on the left to the right, I'm going down. That's not what we want. We want increasing. So as we read this one left to right, it does go up. So F is your best fit for this one, right? Always increasing. Looks like that. Exponential function that's always decreasing. Okay, so that's the C, right? It's always decreasing. Quadratic function. All right, so our quadratic functions, we have two options. We want the one with a local maximum. Ooh, that's an interesting word, local maximum. Okay, so this one right here is technically going up forever and ever and ever. Right? We don't know when it'll stop, but it does have a low point. So this is what we would call a local minimum. So then this one technically would keep going and going. So we don't necessarily know when the bottom is, but we know what the top is. So we do have a local maximum. So local maximum would be E. And I'm going to put a little star right here. This is where the local maximum is. A quadratic with a local minimum. All right, so local minimum. So we do have a minimum. That's A. All right, so now we're down to the two linear functions. We've got this one and we've got this one. We want the linear function that is always increasing. Okay, read your graph from left to right. As we go from left to right, we are going up. So this one is B, boy, always increasing. Whereas always decreasing would be this one that's going down. So that's D, dog. All right, flippity-doo-dog. Now we've got some vocab practice coming our way. Which is the only type of function below that has an asymptote? All right, so if you look at your little cheat sheet here, the only one that has an asymptote is exponential functions. So exponential. Which is the only type of function below that could have a local maximum? All right, so those are those parabolas, right? Those quadratic functions, they have maximums and they have minimums. Should have added that yesterday. All right, so quadratic functions have maximums and minimums. Describe the end behavior. So that was this last section down here. I feel like that's the most complex. It's got some real fancy math symbols going on, so just bear with yourself as you get used to it. You'll see it a lot in algebra too. All right, so this first function, it is going up. It's got an asymptote, so this reminds me of exponential. Okay, so here's this notation. As x goes to negative infinity, so what this is in fancy words, right? This is just saying what's going on the left side of your graph, right? As x goes to negative infinity. So the x-axis, as we're out here on negative infinity, what's happening on the y-axis? All right, so when you look at the y-axis over here on the left, it doesn't seem to be dipping any lower than -3. All right, so on the y-axis, all right, that's what we're asking for. On the y-axis, we are getting close to -3. All right, as x goes to positive infinity, so as we go to the right-hand side of the graph. Okay, so as we go to the right over here, let's focus on that. So what's happening on the y-axis? Okay, so this arrow, what does this arrow tell me? This arrow tells me that it's going to keep going, keep going, keep going, keep going to the moon. So our y doesn't have an end in sight, right? This is just going to keep growing, 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 growing. So we would say the end behavior on the right is that it just keeps shooting off to infinity. Whereas on the left, it was approaching an asymptote. All right. Over here, it's U-shape, so that is quadratic. All right. As x goes to negative infinity, so we're going to focus on the left-hand side of our graph. All right, so on the left. So look at the left arrow. Where is that left arrow pointing? It's pointing up. That means it's going to keep going, keep going, keep going. So if it keeps going, then it's going to head up to positive infinity. All right, we're going up. As x goes to the right, as x goes to positive infinity, so on the right, what's happening on the right arrow? Again, it's going up, 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 up. So it's going to keep growing and growing. So it's pointing up on both sides, up, up. All right, here we have a line, so we call this a linear function. All right, so let's look at the left-hand side of our graph. So if we're over here on the left, which way is our arrow pointing? Our arrow is pointing down, so it's going to keep going down. So down is negative infinity. All right, we're going to keep going down towards negative infinity. All right, as x goes to positive infinity, so now let's go to the right arrow. All right, so on the right-hand side, again, it just keeps going up, 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 up. So we're going to keep going up forever. No one's going to stop me. You'll notice that on the end behavior examples, the only one that has a stopping point is the exponential function, right? They have the asymptotes, so it's going to stop you on the y-axis. But as far as quadratics and linears go, there's nothing stopping them. They're going to keep growing and growing and growing. All right, next up. Which is the only function that might have end behavior such that x approaches infinity, or as x approaches infinity, so as we go to the right, f of x, right, that's your y, approaches 4. Remember, the only one of these that has a bound on the y-axis is exponential. So exponential function is the only one. All right. Which of the functions below have this end behavior? Okay, so as x approaches negative infinity, that means on the left, the y-axis goes up. All right, so on the left-hand side, it's pointing up. As x goes to the right, our graph also goes up. So on the right, it's also going up. So which picture has up, up? Well, that could be a quadratic. All right, how about this one? So on the left, our graph goes down. All right, that's what this is saying. On the left, the graph goes down. So I'm going to draw over here on the left-hand side an arrow going down. Over here, as x approaches infinity, so on the right, our graph goes to positive infinity, so our graph goes up. So on the right, our graph goes up. So the only function that has down on the left and up on the right, I can't draw a straight line, is linear function. All right, quadratic has to have the same points, right? It's either going up, up, or down, down. Exponential is going to have a roadblock. Linear, one side's going down and one side's going to be going up. All right, how about this last one? So as we go to the left, our function points down. So on the left, it's going down. On the right, I guess I should write that word right there. There we go. On the right, our graph goes to negative infinity down. All right, so if you're going down on the left and down on the right, that means you've got a quadratic function. All right. One more page. Okay, so now we want to match the equation to its best description. These equations need to be simplified though, so we got to do some multiplication right here. So this is 2x squared plus 3x. All right, so if we've got something squared, let me go back to my cheat sheet from yesterday. If we have something squared, that is quadratic. But we have two options, local max or local min. Okay, if we have a max, that means it is pointing down. And if we have a min, that means it's pointing up, right? Because we've got that minimum or we have that maximum. So the way we know is by looking at that front number, right? The A is that very front number. If it's positive, it's happy and it's going up. If it's negative, it's sad and it's going down. All right, so when we look at our options here, this is a positive A. So positive A means it's pointing upwards. All right. This one, we need to do some distribution to get it cleaned up. 3 times 1 is 3. 3 times negative 2x is negative 6x. And then we have this minus 4. We can combine the 3 and the negative 4. So 3 minus 4 is negative 1. All right, so this is negative 6x minus 1. So all we're doing, I guess I could write up here for you, is combine like terms. All right, we're cleaning it up. We're not solving for anything. There's no opposites here. Okay, so it's just an x. Nothing is squared. I don't have any variables. So if it's just an x, nothing is squared, that is linear. Linear. Oh, okay, so we have options. Is it growing or is it decaying? All right, so we have to look at the slope. Look at the number attached to the x. Look at the number attached to the x. That's right here. If it's negative, that means it's going down. It's decaying. All right, so we have negative slope. Negative slope. Over here, we had a positive A. All right. This one, we don't really have to do too much here. I think I can figure out what it is because the variable is now an exponent. If the variable is an exponent, boom, that's exponential. All right, so is it exponential growth or exponential decay? That's when you look at the base. All right, it's getting cut in half. So it's getting cut in half each time it's decay. All right, it's going to be coming down. Alrighty, next one. Again, the variable is an exponent. If the variable is an exponent, it's either exponential growth or exponential decay. So it's none of those. All right, so look at your base. This is 2, so that means it's doubling. If it's doubling, then it's growing. All right, next one. Look at that. The variable, right, is x squared. So when I look over here, x squared, that's going to fall under quadratic. Okay, so is it a local max or local min? Check this out. It's out of order, right? We want it to be in order. We want the squared term first, then the x, then your constant. So when you look in the front here, you have a negative a. If it's negative a, it's a sad parabola. That means we do have a tippy top. We've got a local maximum. All right. 1/2 x minus 1. It's just an x. Nothing is squared. I don't have any exponents that are variables. So we are linear. Get rid of those. Growing or decaying. Now, be careful. 1/2 does not mean decay for linear. one